Okay, welcome back. So this is the last boutique lecture, and it'll include actually a little bit of just reflecting on what we did over the course. I find it's useful to sort of say it back in a slightly different way at the end, I hope. But we're going to talk today about a little bit about soft robotics. I don't want to say we're going to cover all that there is to say about soft robotics. And its implication for manipulation and for tactile sensing. So when we started way back, lecture 2, we talked about robot hardware, we talked about the EWA, why the EWA was cool. I also showed a bunch of cool hands, right, including some very unconventional hands. One was made out of jamming grippers, like coffee beans, right? And some of them are unquestionably soft, right? So this was just one of the ones that I showed was doing pretty dexterous manipulation with pretty floppy fingers, right? So I want to explore with you today, what it is about being soft that could be good, what are the pros and the cons, and give you a quick sense of what's out there and what people are doing. So, I've been interested in soft for a pretty long time, but there were a few, I think it's kind of a punctuated evolution of my relationship with soft. And in particular, there were a couple results out there that really captured my imagination. This is one by Alex Alsbach, who, oh, I didn't mean to leave the music on, sorry for that. I normally turn those off, okay. He was working at Disney, and he built, this inflated, Dynamixel sort of robot with inflatable paws and an inflatable chest. And there was something, he showed this at a humanoids conference that I was attending, and there was just something about the way that this is interacting with the little Mickey Mouse toy and the Apple that at the time when robots were going, with their rigid hands, and this seemed so natural to me. This really captivated me as like, that's having interactions like that with the world is potentially game-changingly different, in my opinion, than having these rigid objects that are, that are trying to do exact perception and trying to be accurate, right? This is just a very different way to interact with the world. And Alex went on to build hands based on this kind of ideology. You could have bubbles as fingers, and you can imagine scaling that down. And actually, when TRI started, I was so captivated with this that I immediately recruited Alex to come start a soft robotics team at TRI. So he's the one that's behind the soft robotics stuff that I've shown you from TRI, and you'll see a few more of those. And he's just down the street. He was in the building earlier today, and he's a great guy. So, but this really, for me, was one of the first times where I thought, geez, it's not just that that's a cool technology, but that really, maybe I'm programming my robots wrong because we're touching things, with these rigid fingers. And I should really be embracing the softness sooner rather than later, because it might change my computational pipeline. Okay. So there's a lot of things that people say about soft, and it's like kind of, every soft robotics paper sort of starts off with a kind of a list of great things about being soft. But some of them I think are said a little too quickly, or I just want to dig in with you a little bit about what it's good and bad about being soft, right? So. Benefits of being soft, I guess, okay? So one thing that people often say very quickly is that soft robots are inherently safe. Ironically, I had a conversation today about someone telling me how they were injured by a soft robot, but that was partly in response to me saying I was going to say this in lecture. So Okay, so yeah, but this is a standard sort of you know, motivation for being soft, is that you can just sort of be inherently safe. But I want to question that a little bit and just make sure we understand that. Another big one that people talk about is that soft robots can be inherently less dependent on perception or geometric models, somehow be robust to, in particular, people talk about the geometric uncertainty, right? So what do I mean by that? So like the Mickey Mouse mouse little stuffed animal is not something that is like they have an accurate point cloud of, that they're doing, you know, rigid point cloud registration of and estimating its pose in order to, they've got a simple scripted, you know, motion of the hand in that example, or the apple, you know, and they just kind of put the object roughly in the right spot. And they could have put a different object roughly in the right spot, and it would have done pretty much the right thing, right? And that is probably quite different than would have happened with a rigid hand. But again, I think we should dig in a little bit to why that happens, or how broad that claim deserves to be, right? There's lots of other motivations out there. Some people say, you know, soft has the potential to be very durable. I think we're going through this sort of revolution of fabrication technologies, and some of the early ones weren't that durable, and but there's now, you know, you'll see videos of people driving over their soft robot with a car or hitting them with a hammer and stuff like that. That's sort of standard fare for a soft robotics project, right? I've seen them, you know, you put it on the barbecue and they light it on fire, and it's like, oh, my soft robot still works, right? That's cool. You know, I think there is a real potential for them to be low cost, you know, possibly even, you know, self-healing. You know, I don't have as much to say about the fabrication part of it, but I do think that is an interesting motivation, and I think we are seeing, I mean, we have seen over the last 10 years, and we'll continue to see a revolution in fabrication that I think does strongly motivate soft robotics. But let's think about at least some of the first two a little bit more critically from a modeling and dynamics and control point of view, okay? And the way I would love for you to think with me about this for a little bit is actually, I think there's a very simple model that can get pretty far, okay? So let's say I have an object to be, maybe it's on wheels if you want to think about it. I want objects that can only move horizontally, so we'll call this our manipuland. Okay, and we'll have maybe our hand. We have two hands, we'll do bimanual stuff. Okay, and because I like to keep the geometry simple, I'll have a point finger. Right? And these things are only moving, the only degrees of freedom are left to right of the hands, right? And I want to manipulate the manipuland, okay? And maybe you can see where I'm going here. I want to compare this version, which is a pretty rigid picture, and I'm just driving the hand around, with the same picture, but now if I have my point contact here, and I attach my finger to my hand with a spring, okay? And maybe it's even a spring and a damper if you like your mechanical drawings a little bit more complete. I could put a damper here between my hand and my finger and my manipuland, right? Object is a little shorter to write. Okay. And let's think a little bit critically about the differences between those two systems, right? Can we actually say that a system that has a spring in it is inherently more safe, is inherently more robust to geometric uncertainty? Does it have all these attributes that we say? Okay, so if I were to take this and write my rigid body mechanics for either of these two, and I were to now bring this hand in contact with the manipuland, then what happens at the moment of contact? Let's maybe think about first the moment of contact. The rigid model is going to have an impulsive event, right? If this is strictly rigid and you're not allowed to penetrate, and you have a velocity before the contact and you're not allowed to have velocity after the contact, then you must have had an impulsive collision at the moment of contact. It could be elastic, it could be inelastic, but there's no question that something happened in 0 time in order to keep you from going inside the object, okay? So the rigid has an impulsive collision. Now in this one, the purely soft one here, if I have, a point finger here that is massless, if I assume for a minute it's massless, right? This is like assuming a spherical cow. It's kind of, it's very useful, but a little silly. Right? Then if this is massless and I have a perfect spring here, then I don't have an impulsive collision, right? Okay, so you could argue in that sense that it might be, maybe it's better for the object to not have that impulsive force that hits it all of a sudden, right? You can make those collisions larger or smaller depending on your your momentum, I guess, at the moment of collision. But it is true that if you can remove that mass completely, then you get rid of the impulse, okay? And really, I want to make sure that I'm clear. This is an artificial scenario. This never actually happens, right? Really, we always have something that looks more like this, right? And we have some mass of my finger here, and we have some imperfect spring that has a stiffness K, maybe a damping B, let's say, and I have a mass of my hand here. Okay, so this is, this is the perfect model case, but I think in reality, we should be thinking rather, what is the relative mass of the finger, of before the spring and after the spring. Okay, and then what is the relative spring constant, or relative stiffness? How large, how stiff is my spring, right? And that of course only matters relative to the mass again. To give you a total resonant frequency or all the characteristic dynamics are going to depend on the ratios of mass and the spring constant. Okay, so I think the analogy to be more fair would be, how much benefit is it to have my mass of my finger particularly low and my stiffness low, compared to the mass of my robot, right? And you can tell that in a design like this, right, this is trying to make, the mass of the finger look more like the mass of the latex making the bubble, right? And the stiffness quite soft, where the bubble deflects, easily and potentially over a large deformation before you have the immediate effects of the hand, at the moment of collision. That part seems reasonable? Okay. What about at steady state? Like, what about my steady state forces? Like, once I'm in collision now and I'm, applying some force on the hand here, from my whole robot, what forces can I apply in steady state? how do the masses of my finger and the stiffness of my spring and relative to my hand affect my steady state forces? They don't, right? Right. At some, once I've hit a rest length of my, my new rest length of the spring, then the forces I'm applying here are being completely imparted here, right? So in steady state, there's no difference, effectively. So if your robot has enough strength to crush, I guess, Mickey Mouse, right? Then your soft robot has that strength and your hard robot has that strength. So inherent safety maybe is not fair at steady state, I would say. And I would say maybe even more importantly would be that springs can be dangerous. I mean, I don't, like you can store energy in springs, right? So you could potentially take a pretty soft looking thing and kind of load it up, make it into a catapult, and fire off some pretty large forces if you're not careful, right? So I always balk a little bit when people say that soft is inherently safe. I think you have to do a little bit more to get safety from soft. Dissipation, I think, does inherently pull energy out of the system. If you have damping in your soft element, which most soft things do, then that pulls energy out, and that is inherently a stabilizing and maybe a safer point of view. But I think stiffness alone doesn't make you safe, right? It's kind of a strange thing to write, but I'll leave it. Okay. There's a trade-off, of course, right? So if you do make these things soft, then you can reduce your impact impulse, right? You don't change your steady state. Dissipation can remove, but you give something up if you add a soft spring between your actuators and the world, right? What do you give up in the linear systems sense? There's a word that some of you know, I'm sure. Yeah, control. I mean, not officially controllability is Boolean, but you could somehow reduce your controlled bandwidth. Would be the right. Right, so what do I mean by that? Let me just finish the thought real quick. But if my goal, in the linear system sense, if my goal is to make this execute, let's say, a sine wave trajectory, okay, and I'd like to, look at what my finger has to do as the frequency of that sine wave gets larger, right? The work that I'm going to have to do goes up fast if I have a very soft actuator. And what that implies then is that if somebody surprises you with a disturbance or something, your ability to respond and accurately control the high frequency behavior of this system is poor, right? Your control authority at high frequencies, I guess, is what really gets you, right? Because you've given up something with the softness, right? So if you have a hard robot, infinite bandwidth and control authority, then you should always be able to outperform a soft robot. You could always act like you're soft, right? So in practice, when we're putting this in, it's somehow admitting that our bandwidth is in practice limited in a meaningful regime. Sorry, yes, please.
I'm wondering if there's another side of that coin.
Yeah.
Whether the bandwidth that's required to drive a soft robot is also lower than in the stiff case. Like thinking about the task of grasping an egg with a rigid robot, you need infinite bandwidth to not crack a perfectly rigid egg.
Good.
But you could probably do a 1 hertz control loop with a soft robot if you had a really soft spring and still grab the egg.
Good. So there was a comment for those hearing about what if I'm trying to hold an egg, right? And I have an egg-like example coming in a minute. Yeah, is it that maybe if I have a soft robot, the requirement on my bandwidth is less, and therefore I can get away with the softness? Yeah, I think I agree with the spirit of your comment. I might say that the task demands a certain amount of bandwidth, and many of the tasks we try to do with soft robots don't require high bandwidth, right? I might say it a little bit differently, but those two do play together. I think the place where soft wins is when your bandwidth requirements are low, and actually probably for a lot of things we do in manipulation, our bandwidth requirements are very low, right? Certainly holding an egg, I wouldn't think would be a particularly high frequency thing, right?
But if your contact events are delta functions, then what you need is like a really high bandwidth to close the rigid, like a
Okay, great. So I said if you had a perfect stiff robot, couldn't you always do better? Okay, and yeah, good. And so you're pointing out that a contact event is like, ideally a delta function in practice because things aren't perfectly stiff. It's going to be a very short time event, right? So you're right. I think you need very high bandwidth to perform incredibly well through a contact event, right? Like exceedingly high bandwidth. And so therefore, why try? Why not let the mechanical system handle that initial contact event, and then you do your thing after the fact? Completely agree. That's a very good way to think about it. Okay, so in this picture, I know a very simple picture, but I think hopefully a helpful picture. So we talked a little bit about the safety claim and maybe the bandwidth we mentioned quickly here. Is there a sense in which it's robust to geometric uncertainty in this picture? Right? Is one sort of more or less robust to geometric uncertainty? I mean, that's a claim it's sort of easy to make when you see a video like this. How does it play out in this simple diagram? Yeah, please.
I'm thinking about like the case where you've already established a grasp, and I'm thinking about varying the shape. In the soft case, I would expect some sort of like continuity properties on the force. Like if you established a grasp and you change the shape, the force should only change proportional to the change in shape because you're like, just changing the length of your spring, and that should change the forces continuously. But if you had a completely rigid grasp and you established it and you shrunk the object a little bit, you would expect a discontinuous change in the forces.
Okay, good. So your thought experiment here, to summarize, is that imagine I'm in contact and I've made a contact with my rigid or very stiff thing, and I suddenly shrunk or expanded the geometry. That's nice. Then this is going to have. I mean, again, I guess this never exists, right? So we're in the very stiff case is more thoughtful. It could have a large reaction force that gets generated. So in some sense, your sensitivity of your controller might be higher because of this geometric uncertainty, right? I mean, I think even in this super simple case, you could, if you thought this was at a 2 centimeter wide brick and it's actually a 1.9 centimeter brick, you could end up right here and just try to lift it up and completely miss. Or if you were trying to push inside it, you would be exerting very large forces and fighting against it. I agree. But I actually think the bigger case, let's see. I want to distinguish softness from position and force control. These are comparable ideas, and they're separable ideas, right? So once we have this idea that everything is, at least maybe the stiffness is very large if I have a KUKA with a metal exterior, but there's a stiffness there, and we always put at least a rubber pad or something between our metal and our contact, right? Position control, I think, is going to be vulnerable to geometric perception errors, but force control is pretty good, right? We saw examples of flipping up boxes without really estimating anything, right? And I think it's healthy in this picture to think about this as a force sensor. In fact, most force sensors are somehow, having some material of known stiffness, and you're measuring the deflection of that material. If you have a known spring stiffness and you can measure this deflection, then you've got a force sensor. Okay? So I think in this simple picture, you can achieve robustness to geometry just by being in a force control mode instead of being in a position control mode. And I think maybe in my mind, the argument for geometric robustness is somehow not as great. I could do this. Maybe my ability to do force sensing might be more or less depending on K. But I don't think I need to be a bubble to be better at immune to perception errors here. So let's make our diagram a little bit more rich, because I do think geometric robustness is a real thing. But I think we need a more expressive picture to see it. Okay, so I hope you're okay with these sort of silly diagrams, but okay, let's say I've got my hand, my object, my hand here, okay? And instead of one point finger, let's make an entire array of point fingers. Okay, they can have dampers too, and on this side too, of course, yeah. Now things get more interesting. Right? So let's say I start squeezing my hand together, and let's say I'm large K, the stiff regime. And I don't know, in this case, I haven't even given my hand the ability to do well with a lot of geometric information, or if I just had geometric uncertainty and I was choosing my pose as I was coming in, you could get a similar picture. But let's think about the type of contact that you'd get if you just start squeezing your hand together and you have a pretty stiff set of springs, right? I think it'd be pretty easy to, I'll exaggerate it here, like I've got some object here. It'd be pretty easy to get in a situation where you're in contact sort of in one or two places here. The first part of your weird finger-looking thing is in contact, and the rest of them, there's sort of no contact, right? Is that picture clear? Okay. Now, the picture, of course, changes if I'm in a very soft regime. You could imagine, for some stiffnesses and some objects or whatever, being in a situation where the same forces that produced this situation in a stiff regime could produce this very different situation in a soft regime, right? Where you might have a larger force there because it's because it's compressed the spring more, but I'll have forces everywhere, right? Maybe proportional. Yeah, I should be more careful to make them proportional, but I think you get my drift. Okay, so why does that matter? Let's say we're going to start lifting the object up, if our goal is to lift the object up. Okay? What amount of squeezing force do I need to apply in order to successfully lift the object up? Right, I need to have enough vertical force to fight gravity, right? Every one of my contacts is limited by friction. So at every point of contact here, I've got some friction cone, right? Maybe they're uniform everywhere in this first example here, okay? in order to successfully, I've got the same thing happening on this side, right? In order to successfully achieve liftoff, the vertical component of my force coming up here, which has to stay inside the friction cone if I don't want to slip, is going to be limited. My force tangential is going to be less than or equal than mu of my force normal by the static friction law, right? That's my friction cone. Okay, I'm going to have to squeeze hard. In this regime, I might have to squeeze hard in order to achieve enough friction in order to get up high. Okay. In this regime, where I have more possible contacts, I can potentially, even with the same material properties, the same friction properties, I could potentially squeeze less to achieve the same liftoff. Okay. Now that could have stability implications for in a number of different ways. Okay, but it seems at least indicative that maybe this would be a better grasp. I think the real picture is actually more subtle than that, right? I kind of tried to pick arrows to draw that were roughly landing on the normal surfaces there. But I've also got some contacts potentially here that have friction cones that are using the same coefficient of friction, but potentially on very different normals, right? And I think actually the world of possible contact forces opens up pretty quickly, right? So now I'm firmly in the camp where if I can contact an object like this with like a whole, in the continuum, a whole patch of contact instead of a point contact, then my ability to manipulate the object seems improved, right? Let me be careful. You could still argue the counterpoint that you've given something up, right? If you wanted to somehow explicitly control the contact forces and you're making contact in all these different places with all these different normals, then to be able to regulate exactly the normal force might be almost impossible now because you wouldn't be able to know exactly what forces. But to achieve some sufficient force to pick it up or to resist a wrench, that would be another standard thing, would be if someone came and knocked this, how likely is it to pop out of my hand or something like this? A grasp that has substantial patch contact seems like a better grasp most of the time. Okay, so I think, for me, the difference from point contact to surface, or people call it patch, contact patches, contact, is a really big deal. And I think that's where a lot of the benefits of softness for geometric robustness and the like come from. And I think it's what kind of captured my imagination when I saw these videos, right? Is that you just really didn't have to know the pose of the object. You didn't even have to know where it was, but you're going to have this like huggable, loving embrace almost automatically with like an open loop arm motion, right? It's pretty good. Let me go out of order because I screwed up. So I guess one more point before I go on to the sensing aspect of it. Let's compare, back in these pictures here, maybe I'll work with this one. Let's compare sensing or stiffness of the spring, let's say, right at the skin versus something more distal, right? So I talked about Iwa having elastic joints. And when we talked about, and some of you have even asked in your project, how do I do contact sensing? How do I know when I'm in contact with the wall, for instance, if I'm writing or something like this, with the Iwa? And the answer is you look at the joint torques, the external torques on the joint. That's where your contact sensors are on Iwa, right? You could, of course, take your Iwa and put another sensor at the end or in the hand or something, but by default, the Iwa gives you some ability to do it in the joints. Okay, so what is the picture difference here? So maybe I have my skin, if I will, down here with a low mass and a K here, and then I've got my finger or my distal links, and then I have my my elbow or something up here, or my main forearm, a more distal link. Right? I'm still just thinking about the one-dimensional, easy to think about mass spring damper sort of case. My claim is that if I were to put some sort of rubber tips or something on the end of the EWA, then I can do some amount of force control and sensing, and people do very successfully with EWA, right, using this as my force sensor, right, using the fact that there's a stiffness in the joint, and this is my force sensor. And I'd like to sort of contrast that with if you were to try to put your softness and your sensor more co-located with the contact, right? And it's not, it's a subtle argument that talks about bandwidth, it talks about all the things we talked about, and you can do it in the linear systems sense. But I think overall, there are, I think, advantages to having a contact sensor that is more co-located with the actual event, and keeping your actual initial contact mass very low. So this is something that when I showed you this video before from Terry, where he was using this bubble sensor that I was talking about to do writing, right? He had ignored the EWA joint sensors and was just demonstrating that using the skin as a contact force sensor was sufficient to close a control loop that was allow him to write on the board, right? So I think our tactile sensor's ability to do that, and how do we close feedback loops, that's a growing technology, but I think it's an exciting one. I think we can potentially move our softness and our sensing closer and closer to the point of interest. Okay. That's just like a, one way to think about softness, and hopefully a helpful one. Let's think about the sensing aspect of it. So we have amazing skin, and I actually put a picture of like the skin towards the end. We'll talk about what's missing from our robot sensors, but I guess my introduction, I studied it back when I was a grad student. I was in the neuroscience department, right, and I took the classes on the basic brain and cognitive science classes where we learned about the sensory system and all of the incredible sensors you have in your fingertip, right, and everywhere, but especially your fingertips, right. So what are the possible signals we could get out of a tactile sensor on a robot? I mean, I used to, when I was working on walking, I would have been happy if I just had a reliable binary, contact, no contact. Binary switch. We did a lot of work on walking, just like, if you could just tell me with any higher accuracy when my foot hits the ground, I would already be happy, right? Maybe that's still a little bit true today, okay? We've implied here that, and I think a common request would be to have some sort of force sensing from your tactile sensors, right? And I think there's a characteristically different amount of request from a sensor to give a normal force versus shear force. But there's other things too, right? You can, people have built robot sensors that try to estimate, temperature. To estimate, to try to, we could talk about the physics of it, but to try to somehow recognize texture or roughness, for instance. These are all, if you wanted to, like, if I reached into a toolbox and wanted to find, with my, I can't see inside the toolbox, and I wanted to, use my exquisite tactile sensing to find the right wrench, let's say. You know, if I feel something that doesn't feel very metal, I mean, metal feels cold and has a certain roughness, and I've got a strong signal, not just from the geometry, but also from all these other signals, right? You know, so this would have been probably the beginnings of my list a few years ago. But something really did change, you know, fairly recently, where I think more and more we're thinking about, you know, these are all things that you might sort of think about when you think about tactile sensors as measuring a point, okay? But if you like my silly diagram at the top there, right? I think there's really something to be said for thinking about tactile sensing as a geometry sensor, okay? And possibly even a dense geometry sensor. And that was a pretty big change for me to think, you know, maybe even if I'm buttoning, oh, I don't have any buttons on this shirt, this is, but if I had a shirt with buttons and I wanted to button it, right? You know, what do you think you're using with your fingertips? Are you trying to estimate the forces that you're applying to the button? Or are you sort of getting a sense that the button's going through the hole by virtue of feeling some sort of geometry? I don't know if I completely know the answer, but it feels like a pretty good geometry. It feels like geometry is pretty important in a lot of the things that, the thought experiments that Ted Adelson had me run through when we started talking a lot about this. And Ted, I think, had a great impact when he introduced this, you know, geometry view of tactile sensing, which I'm going back to my, here we go, right? So Ted introduced this, well, you know, with chemo, and introduced this sensor GelSight. Many of you probably heard about it, but let me just sing its praises for a minute, okay? So basically, they asked the question of, you know, what happens if I put a camera behind the skin? How well could I do with that? And how could I make that really effective, okay? And there's a couple subtleties about making that effective, right? So one of the things that makes that effective is you'd like to have the camera worry about the geometry of the contact, but not worry about all of the RGB complexity of the world, or the lighting conditions of the world, or anything like that. Okay, so what they did is they made this small gel layer, hence GelSight. They found a nice way to paint the coatings, the top layer of this, so that when you depressed, let's say an Oreo, hypothetically, onto this gel layer, the image from the other side was a beautiful rendering of the geometry of the contact without all of the complexity of lighting conditions or you know, the complexity of sort of real world vision, let's say. So that's a reasonable thing to try to do, and what they showed was that it had a lot of really nice properties, right? So there's in Ted's lab, there's all kinds of different goos or whatever, and it's super fun. You know, you can, there's enough of it floating around MIT these days, you can probably get your hands on some and just start putting your own finger and see, you know, put a dollar bill on there, put a, you know, you can see like the hair on your finger or the grains of a dollar bill through this thing. And one of the reasons that it's nice that the RGB signal doesn't come through is that they were at the time doing strictly geometric reconstructions using photogrammetry. So in a controlled lighting situation with the RGB of the world excluded, they could just put a red, green, and a blue light in known locations and do sort of a classic computer vision trick for extracting depth from those, that now colored image, okay? And it's just awesome. Like you could just see everything, you know, this beautiful geometry sensor. Okay, that's a pretty big pad to be like sticking on your fingertip, but people have been scaling it down, and I think the vision is that we'll have these things scaled down. So if you have dense geometry available, available in your fingertip, then I think it connects back pretty quickly to all of the things we already talked about in the geometric perception lectures. Right? So as an example, remember we talked about DART, where we had point cloud measurements coming in. We talked about non-penetration constraints, you know, and then we did our real-time pose estimation and tracking. Right? That was just one of the algorithms we talked about in geometric perception. And that was based on this idea of having a depth camera that was looking at the scene. Right? We got our point cloud. We also had our free space constraints, all these things you hopefully remember a bit about from DART, okay? If you have a dense geometry sensor in your fingertip, then it's like you just have one more incredible depth sensor available inside your finger, okay? But it's, you know, it's got a short maximum range. That's okay. I mean, that gives it it's a, you know, lovable limitation, I guess, right? But it gives you, you know, information that's not available from other sensors. So, you know, when we started playing with GelSight with TED, that was the point that we tried to make, Greg made, was that if you have a dense geometry sensor in your fingertip, it snaps right into the geometric perception pipelines, and you can do pose estimation, tracking, you name it, directly through your combination of head-mounted sensors and dense geometry sensors in your fingertips. So as an example of an application that was enabled by that, if you wanted to do an insertion, right, that required some kinematic accuracy, and you wanted to track the position of the, let's say, screwdriver that had to fit in a relatively small hole, then, I mean, the first thing that happens, we've talked about before, is that whenever you start touching things, your head-mounted cameras often quickly get occluded by your hand. But even more so, you can get more accuracy from these very local, you know, dense sensors in order to take out any of the remaining uncertainty, sort of, and do finer scale insertions.
What's the difference between the left and the right?
This one's ignoring GelSight, using GelSight and ignoring GelSight. It maybe wasn't as profound as we had originally imagined when we made it, but this one is, you know, basically missing the hole, and this one's going to make the hole. Now that one did. Why did it make the hole? I remember it being more profound, but that was the with and without GelSight. That's one in a series of works that people have done with GelSight. Alberto's lab has taken GelSight and made a more robust version of it in GelSlim. That is you can see these sort of similarly architected sensors. GelSlim has got like a really, I mean, we used to rip the GelSight off the finger all the time. It's kind of, I mean, again, I love GelSight, but let me just make the point, right? So it's kind of frustrating to have like this exquisite geometry sensing right here, okay? But then if you happen to reach in and it doesn't hit exactly where your sensor is, then not only are you blind, but you rip the sensor off, right? So that was kind of frustrating. And that was just the state of the, you know, state of the sensor when it started. You know, this one's got a much tougher fabric. It's removed all of the, you know, I think the frailty on the edges. It's still limited to making contact on the sensor. The geometry is also different. So the photogrammetry, I believe, is gone in this version. You know, Rachel can correct me if I'm wrong, but I think they've switched mostly to doing depth reconstruction using deep, deep learning approaches to reconstruction because the photogrammetry required a particular geometry of the red, green, and blue sensors, and that was constraining in the geometries that you could build your sensors. And this, I think, used a longer throw and gave up on the strict photogrammetry reconstruction. Is that true? Yep. And the work here, by the way, is also awesome. I mean, not only did it use the tactile sensors, but it used it to do cool things, showing feedback control of, you know, where objects being moved were observed as being, requiring different action, and it even has like you could say a task and motion planning level at the top to be very robust. This sensor here is also inspired by GelSight. It's a different approach. Again, living with the two-fingered gripper is kind of limited but beautiful in what you can do, right? You can do a lot of things with a good brain and a simple hand. On the inside of this is a dot pattern, okay? And we've got a depth camera inside here, so we actually have a Connect, it's a PicoFlex inside here, okay? That is actually doing explicit depth reconstruction, and then we put dot patterns on here in order to get shear and other forces. And this is super robust, and we've done a lot of cool manipulation with it, included, one of the things you do is you say, I'm immune to the transparency of wine glasses, and I'm subtle to the touch, so we can do things like stacking wine glasses. So I do think we're in this sort of series of very cool advances in sensing. The geometry sensing is part of the story, but we do actually have these other types of sensors, or let's say camera-based geometry sensing is only part of this. I told you about Punyo, this is just the hand on Punyo, and we have this sort of bigger ambition of building out full, Baymax-like humanoid that's making contact all over the place and using tactile sensing all over the body. This is the project that Alex is leading at TRI. And just as another example, right, there's a whole bunch of different ways to measure geometry or force, which of course, if you know the stiffness of your sensor, are related. This one is an inductive sensing in the chest, actually. So when you are picking up a massive water bottle with your chest, then we have a sparser. I mean, humans also have a lot more density in their tactile sensing in the hands than in the other parts of their body. And so I think a simpler, cheaper technology is warranted, okay? And even along the arms, we're just using pressure sensors in the air pockets covering the arms. Inductive sensing has been used, capacitive sensing has been used, resistive sensing, basically every possibility, right? Force sensing resistors have been used often. They all have their different, pros and cons. I'll try that one more time just in case I get lucky, but maybe I don't get to show you the IIT iCub, I believe is this one. Very cool initial sensing skin. I would say one of the most advanced systems level integration of sensing skin technology on a humanoid robot is this from the Italian Institute of Technology, the iCub skin. I encourage you to check it out. They not only built nice tactile sensors that could be arrayed, but they just incredible engineering to make these huge arrays that could be formed to the skin of the body, and they just had like a whole humanoid with beautiful skin, and there's videos of them, applying forces and controlling the robot on a full humanoid. Extremely cool. CSAIL is MIT is a pretty good place, I guess, for tactile sensing. Wojciech's group has also been doing novel tactile sensors, right? So this is one of a series of things where they've basically been sewing dense, I think this was FSR at the time, force-sensitive material into fabric, right? And they have smart carpets now, they have smart gloves, and they have just great instrumentation. I think the possibilities for robots to be completely coated with dense sensors, for humans to have a more immersive, VR, AR experience with these kind of sensors. I mean, tactile sensing is just, I think, finally coming of age. It's actually kind of weird that it took so long. I mean, everybody has known forever how important tactile sensing is. and it just took a very long time. Ted used to say, I've got this great tactile sensor, and I go to the roboticists, and I say, I've got this great tactile sensor, and they're like, we don't know what to do with it. You know, that's great information, and we don't know what to do with it if you gave it to us, right? So maybe, I guess, the roboticists are finally waking up. But let me, you know, I'll finish here by saying that the human skin is actually incredible, and there are many other things that you can do that the human skin does that we're not doing, I think, in most of our tactile sensing yet. So let me just, you know, point out a few subtleties in these tactile sensing. I won't name all of my anatomy anymore. I don't think I could without, I mean, I remember all the corpuscles and Purkinjes and stuff, but just barely. Some of them measure force, some of them measure temperature, some of them measure vibration, right? So actually the signal that you'd get if I were to try to measure the roughness of this, there's a part of it, possibly, that is about the spatial forces that you feel along your finger, and the fact that you have, you know, your skin has curves and stuff certainly matters, okay? But there's also a big part of your signal that comes in the time domain, right? Then you have high frequency vibrations that are actually a strong indicator of the roughness of your fabric and stuff like that. These are things that are totally baked into our human sensing, and I mean, people talk about it in research, but I think they're not mainstream in robotics yet. So I do think robustness is less of an issue now, but it's still an issue, I think. As is surface area, or let's say surface coverage. This story I said of somehow ripping off a GelSight or you know, reaching into the toolbox and having the first contact between my hand and the world be not where my sensor happens to have incredible resolution, but somehow on the edge of the sensor where I had some plastic housing, and actually that's the part that almost always bumps into things first. You know, these are still, I think, practical issues that are getting better and better, but they're still real. Sensing slip is a super interesting one. Everybody thinks if I have tactile sensing, then I can be more robust because I can sense when things slip. Okay? Actually, Francois had a great example of it. He really wanted to close a feedback loop on slip. That was the project with the ABB arm in Alberto's lab. And I remember him saying at his defense, it's just too hard. It's basically like slip happens fast. Slip is an instantaneous event, I guess. You know, you've gone from static friction to a sliding friction regime. And in most cases, with the bandwidth of our sensing plus control, by the time something slips, it's too late, right? So people talk a lot about, so I've seen very few successes of control systems that react to a slip in order to recover, okay? People talk about trying to predict slip. There's a notion of incipient slip where you're like on the verge of slipping and you try to detect pre-slip events and avoid them and stuff like this. But I think it's too much to say that tactile sensing gives you the ability to recover from slip. And maybe in very, like if something slides extremely slowly out of my hand, then maybe, but you know, blocks falling out of my grasp and stuff happens pretty fast. And there are a few others that are, this is kind of just my random list of other things I wanted to say, sorry. But I've always wondered, and people have often talked about proximity sensing versus contact sensing. And there's been projects through the years that pop up and have it produce a new proximity sensor versus contact sensor. So as humans, our tactile sensing is limited, that we don't feel things until they actually make contact with us. Right? Almost. I mean, we do have hair, right? As mammals, you know. So we do actually get a little bit from that, and it's interesting that you should think about what signal your hair is good for, right? I think it's not only for warmth and other things, but you can maybe tell if there's something coming by a little bit of aerodynamics on your hair. You can certainly feel as your hairs bend out of the way. It's pretty amazing sort of stuff that happens here because of this instrumentation at the bottom of your hair follicles, okay? But there's really, I mean, we talked about GelSight sort of having a limited throw at the skin and that being a good thing in terms of making the sensing simpler. But why shouldn't our robots go ahead and detect something before it makes contact? Why shouldn't we bury in our skin things that sense the approach of something, right? The proximity of something. It's interesting. It just seems like an obviously good thing to do, and it hasn't really taken off, right? I mean, I could list a couple possible reasons why. I don't know if people here know why, but I mean, I think it is. I've heard from people that do it that it's hard to make a proximity sensor that works uniformly for all types of objects. You know, like to have something that would respond to a metal and a wood and whatever. Like, you know, a lot of technologies that are behind the skin and are using non-vision based techniques are sensitive to material properties. You know, some things are magnetic or whatever. But I wouldn't be surprised if, you know, in a few years we are sensing contact before it happens. It seems like just an obviously good idea. Okay, so that was I didn't do my chip demo, but you know, I thank you for bringing the chips, by the way. I was just gonna make the point that I could, you know, squeeze a potato chip in a rigid object and it would break, and I could squeeze it in this. I'll at least squeeze it in this. It's the distributed contact point, right? So this is the standard thing, would be the egg. You know, it's good for the egg. It's good for the potato chip. It's not just like I can produce more forces, but it's pretty nice to sort of distribute the load across an entire surface. You know, it's good for the object you're hugging too, right? I can put a lot of force, normal force on this, and the chip's fine. And I've got a few broken chips from playing with my rigid clamp just before lecture, and some grease on my fingers. Yes?
So a question that I have is we started off talking about all of these really cool open loop achievements with soft robots, like the thing manipulating the cube without any sense feedback. What was the gap that led to all of this tactile sensing if we get all these great results just from open loop?
Yeah, I mean, for a long time, and maybe even still today, like the soft robotics journals, wherever, there's like incredible fabrication technology, incredible results. I can hit my thing with a hammer, I can put it on the charcoal grill, and then it says like, control is future work, right? Sorry, I think it's still true. But everybody knows that you should do control. I think like the things you can do in open loop are, you know, enveloping grasps work really, really well, right? But there's a whole bunch of things in manipulation that is more than enveloping grasp. That's been a theme over the, you know, if you wanted to do the type of stuff, you know, even the bottle turning, right? The, you know, the stuff that Rachel was showing, or any number of things we've shown over the term, you got to do something more than just like the open loop stable, right? You want to be able to react to your environment, dig into the toolbox and find the wrench. There's all kinds of motivations for that. I do think that we don't have all those pieces. I mean, deep learning, so geometric perception works well with Tactile once you have dense geometry. You can combine also in a deep pipeline, you can bring your tactile sensors in, especially if they're dense geometry, and you can put them through a convolutional network, and that works pretty well. Yunzu in our group has done some pretty incredible things with that. Other people have as well. So I think it's coming, but we haven't seen, I think, its full power yet. Yes?
So I'm curious, you said we maybe get more capabilities if we have proximity sensing, but I'm just having a hard time imagining what we'd be able to do with proximity sensing that you couldn't already get with like a hand-mounted camera, besides avoiding occlusion.
Good question. So what about proximity versus a hand-mounted camera? But I think hand-mounted cameras have been less useful than I expected. And I think certainly depth cameras have a maximum range and they also have a minimum range. And that minimum range, oftentimes when you talk to the manufacturers, they're like, well, we just never, nobody ever asked us to make a shorter minimum range. That we were always worried about pushing out the maximum, never shortening the minimum. So there's probably hardware improvements that if it became a priority could be done. But even RGB techniques, it seems like once you get pretty close, the RGB signal is just not as good. Maybe your camera's getting blurry, but also just the field of view is very small, right? And then once you're in contact, I think you could start getting local but interesting geometry again. But there seems to be this sort of intermediate space where you're too close for a camera to be super useful. You're not touching in contact yet. Maybe we will have cameras looking out all over our bodies. Right? That's a possible future, and rely on the RGB, and maybe just because the price point of iPhones bringing down cameras and stuff, maybe that's the reason that's the way it's going to go. It's a good question. Okay, the big points. I think you can think a lot about the mechanics of softness, the benefits or trade-offs of softness, even with linear spring mass damper systems. I really think that a lot of people have used that kind of model as to great effect to think about the pros and cons of softness. The real world has more interesting geometry and the like, but a lot of the lessons transfer. And the fact that Tactiles can be a geometry sensor, I think is just a really cool connection to the type of tools we've already talked about. You can do pose estimation tracking, but you can also do shape estimation. There's object detection, all of the sort of classical perception techniques you can think about doing with Tactile. It's a little different because you have very local features as opposed to global features, but the same kind of ideas work. All right, so let me end by just kind of giving an overview, kind of a wrap up of what we've done over the term, just to put a bow on it here, okay? We've done a lot of things. And I appreciate, I sort of feel like the class is taking material that maybe is still sort of like research seminar class, and it's trying to present it as a textbook class. And we're somewhere in between, and there's some rough edges, and I appreciate your patience. But it's pretty fun to sort of be in a field that's kind of on the verge of those two things, right? But let's just lay the landscape a little differently than I did in the chapters, just to think about that, right? So we talked about kinematics, dynamics, simulation, right? That was definitely a big theme. In simulation, I emphasized the signals and systems view of the world, right? And some of you hate that this week. But it's good. But I do think that to scale to very complex systems. You hear from the big players that are trying to build these massively complex systems and have a level of robustness that somehow that way of arranging all the different components together is, I think, a very scalable and robust. Simulink is not a successful product for so many years without reason, and I think in manipulation, everything snaps into. We're seeing that over and over again. So you got a taste of that. I hope you didn't dislike it too much, right? And then we had sort of the manipulator view of the world, right? Where we talked about, the manipulator control ideas from, differential IK to force control and hybrid control to stiffness control, right? That's about how do you move your arm around, ignoring all the complexity of the world, right? Regulate forces and the like. We talked about planning sort of in that view of the world too, about, RRTs, trajectory optimization. Right, and that was, our focus in the planning was about, again, about sort of the robot's view of the world with its eyes closed, right? How do you get from point A to point B? If you've brought in some obstacles, maybe you're going to plan around the obstacles. But it was thinking mostly about the motion of the robot, not the motion of the world. We, of course, talked about a bunch about perception. With a big, I wanted to emphasize first some of the geometry and the geometric perception from ICP, DART, et cetera, for pose estimation, but we also talked about a bit about dense reconstructions. That came up a bunch. I never spent a lecture on it, but it kept coming up. And then, of course, the revolution in perception that's come from deep learning. And segmentation, pose estimation, but also new representations. I think the thing I'm most excited about with the deep learning approaches is that we can get fundamentally, we don't have to go all the way through to pose, and we can potentially estimate much less than a full shape or pose estimation algorithm. Maybe it's just the key points. That was a simple example, but maybe it's just some latent representation that isn't even human intelligible that comes out of a deep learning system, but is enough to do good control. And then when we talked about controlling, moving the actual objects in the world, affecting the world more, when we got deeper into that, the major approach we talked about was RL, right? We did it before, of course, by relatively simple, I'm going to come into contact, close my hand, and go like this. But when we started getting richer emphasis on the control of the environment, we started talking about mostly about RL, reinforcement learning. Right, and all of its different variants. But maybe slightly more general, I tried to emphasize the general awesomeness of, I think, visual motor policies. And whether you get them from RL or imitation learning or model-based RL or model-free RL, right? I think the opportunity to connect, these types of rich, sensing, possibly through novel representations directly to control policies is just so awesome. And it's something that we're going to see more and more of. We talked about high-level task planning. Rachel gave a great lecture last week. We talked about it a little bit early on, from strips and padiddle, state machines, and behavior trees, and then TAMP last week. Actually, I told Rachel after her lecture that watching her, her talk about it, I think, next year, I think this has got to be even a more core piece of the class. I think we got to move it up, and it's just such an important piece of the manipulation pipeline, and to scale to much more complicated tasks. I think I felt really inspired by that, right? So those are, in my mind, sort of the core components that we've been talking about. And we've talked, Tactile and other things have added on, I hope, some elements. But it's, like I say, it's pretty fun to be in a place right now where, it sort of feels like we have a curriculum for manipulation, right? And, those tools will get more and more mature, and the core concepts will be more and more mature. And I hope that maybe, there's value. I hope the value that this class can bring is that trying to put these under sort of the same umbrella and same symbols most of the time, and same code most of the time. So, I think the number one thing I want you to walk away with is that it's a super vibrant research community. It's a super vibrant problem. The number of people in industry that care about manipulation is just skyrocketing. I think the potential for it to maybe to get grand, to shape the future of humanity, the future of work, life off Earth, I don't know. It's pretty important stuff, right? Maybe there are other important things out there too, but this is pretty important, right? So yeah, maybe this will be a foundation for you, and I hope some of you continue on and push on and give us feedback, and so that we can keep making the course better. Good. Well, your turn next. So Thursday we will do the project videos, and I think everybody knows the deal, but I hope many of you will come here to watch with us. We'll do a viewing session. We have the room till 5 if we need it, and we'll get oohs and ahs and questions if you're here to answer them, and we have time, and I'll see you then. Thank you.